All right. Let's go and begin by taking a look at the word problem on the screen. Go ahead and read this word problem for us, if you would, Noah.
A certain two-digit number is divided by 2 more than the sum of the digits. The quotient is 5. The tens digit is 4 less than twice the units digit. Find the number.
Now that second sentence looks pretty familiar. That looks like something we've seen before. Noah, jumping over to the second sentence, it says the tens digit. How are we representing the tens digit of a two-digit number? Help in class? T for tens. Okay. And it also references the units digit. And Noah, how have we been representing the units digit? U. So that second sentence where it says the tens digit is 4 less than twice the units digit, that's not a hard equation to put together.
T equals 2U over 4.
There we go. Were you two thinking the same thing that Noah said? But that first equation, if a certain two-digit number is divided by 2 more than the sum of the digits, the quotient is 5. A certain two-digit number. Well, how have we been representing a two-digit number, Noah? All right, so put it all together now with a little the dramatic pause in the middle. 10t plus u, that's how we're representing our number. So it says that a certain two-digit number, okay, class, that would be 10t plus u, is divided by, how do I show division in algebra, Maddie? Fraction bar. So a certain two-digit number is divided by 2 more than the sum of the digits, then that quotient is 5. At your seat, see if you can figure out what that first equation would be. We haven't seen anything quite like it yet. Maddie's got something. Reckon finished or still thinking? Had a look of thinking on your face. Just want to make sure I read it correctly. Maddie, what did you write? I heard equals 5, so I heard 10t plus u over, and then I didn't quite catch what you said in the denominator, and I heard equals 5 at the end. 2 times t plus u? So if a certain two-digit number is divided by 2 times the sum of the digits? Really close, Maddie. I'll let you make your own correction. There we go. 2 more than the sum of the digits would be t plus u plus 2, and that would be our first equation. Did anyone have that equation? Okay, Noah, you did. Good. Okay, Brecken, what did you have? You had the times 2 as well. So same thing as Maddie. Makes sense. 2 more than versus 2 times or twice. Now that's a pretty ghastly looking thing. This looks nice and easy, but that's horrifying. Thoughts on that top equation? What? I like the way Noah thinks. He's like, hey, if it looks scary, folks, just simplify it. How would we simplify it? Ooh, careful. Can you ever cancel terms? No, only factors. Here's a thought. If we were to put the 5 over 1, all of a sudden now this becomes a fraction equal to a fraction. What do we call a fraction equal to a fraction, class? Proportion. And how do we solve proportions, class? Cross multiply. At your seats, simplify the top equation, and Noah, since you're the one who so succinctly said simplify it, tell me what we get. What do we get when we cross multiply?
5 t plus 5 plus 10 over 10t plus u.
All right, remember, when you cross multiply, the product of the means, which is correct, equals the product of extremes. So equals 10t plus u. So a little review there on cross multiplication. Anyone have this equation when you cross multiply? All right, questions on that. Been a little while. Wanted to make sure we reviewed that. Of course, my lower equation is still just t equals 2u minus 4. That still looks pretty ghastly. Bracken, thoughts on what we could still do with this top equation to make it look slightly less ghastly? I'm sorry, louder so I can hear you, please. Well, I can't take a 5 out of everything. I almost can, except right there I can. So it's a good idea otherwise. There's like t's and u's everywhere in that top equation. That's just, it's slightly disconcerting. Yeah, let's get rid of the little one in each case, right? So what might we do? Okay. All right, so that makes my upper equation, which we first cross multiplied. Now we're kind of moving some stuff around. Now where are we at? Good. All right, and then my lower equation, it was already kind of simple anyway, with just t is equal to 2u minus 4. And suddenly now it doesn't look so bad. So it starts off pretty awful looking. We simplify it down, do a little bit more condensing. Now what might we do, Noah? Okay, so? Good, so we're just going to substitute in place of the t right here to get 4u positive 10 equals, as he said, 5 times 2u negative 4. Continue, Noah. All right? And of course, over here we still have the 4u positive 10. Well, let's go ahead and actually take care of that negative 20. At the same time I'm putting the u on the right. Since the 20 isn't a u, let's go ahead and move that over to the left as to get. And the nice thing about this class is you know this has to work out evenly. You cannot get a decimal. You cannot get a fraction. In fact, you cannot get anything bigger than a 9. You must get, and you can't get anything negative. Because you're finding a digit, right? It has to be either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And in this case, Noah, we get u is equal to 5. So I know the unit digit of my number is a 5. How would I now find the tens digit, Maddie? Good, coming to the simpler equation, the much simpler equation, go ahead and plug the 5 in, and what do we get for our tens digit? 6. All right, so let's think through for just a moment what the equation said. It said that the tens digit was going to be 4 less than twice the units digit. That's how we got the 6. But that first statement said that if the certain two-digit number is divided by 2 more than the sum of the digits, what is the sum of the digits, class? 11. 2 more than that would be 13. What would be 65 divided by 13? And that's what it said it would be. The quotient is 5, so it does indeed check out. Questions on this particular word problem? Then if you try one on your own now, you'll go ahead and work this one. Read it silently to yourself, set up your system, and solve. how many had this system at your seats? This system. Excellent, all of you. Good. Continue. As you finish checking your answer here, bring the u over as a negative u, to get rid of the little one, to get a 2u. I went in and took a 2 out of everything. Anyone else do that? Knock the 2 out? No? You just went and substituted straight in here and distributed the 2? Not a problem at all. I knocked the 2 out, and then I could just do a straight t plus 6 without any distribution. Combine some like terms, divide it away. You got t is equal to 2. Bracken, did you also get t equals 2? Working on it. Once we get the 2, plug that in for the t to get u is equal to the 8. Brecken, checking your work against mine, though again, you may not have knocked the 2 out of everything like I did, but still a substitution here, some distribution, combining and solving should have got us to this point. Questions at all, sir? I think you two said you were good to go. All right, let's go ahead now and practice reducing radicals. We've got 3 ways of reducing radicals, but we didn't get very far on number 3 yesterday. But the normal way we reduce, the most common way of reducing, is to do what to the radicand, class? Factor, which technically is division, so you're not entirely wrong there, but the word I was looking for is factor. Factor up the radicand, and as far as letters, of course, we remember, class, that to take the root of a power, we divide the exponent by the index. And as far as, that's the main thing we'll do. But with fractions, what's the key? We don't want the fractions, so what do we have to do? Take the root of the denominator. You can't read the bulletin board properly. Smaller index is the third one. We were on the second one, Noah. Take the root of the denominator. Class, when we have a fraction in our radical, what do we have to do? Take the root of the denominator. So we're going to practice with those, and then we'll talk about smaller index, Noah, which we barely got to yesterday at all. So we'll spend much more time today working on that final method of reducing radicals. At your seats, you've got your notes out and getting some of these example practice problems down and reducing as much as possible. Once you finish the first three, check your answers and ask if you have any questions at all. If you're good on the first three, move on to the last five. But if you have any questions, make sure you get those questions answered. Reckon perfect on all three? Excellent, great job. That's a good sign. Any questions at all on the first three, or are we good to erase? Everyone good to go? Good to go now. It looked like there was something. Was it the reducing at the end of the last one that everything else was perfect? Okay, good. And Noah's working on the last one. He's like, reducing at the end of, oh, I see now, huh? It's called wisdom. You learn from the mistakes of others instead of making them yourself. All right, for sake of time, go ahead and put your pencils down, even if you're not finished with all of these yet. Let's take a look at the ones you did get done. Again, here, 9 can turn into 27. Now, if it's for a square root, I just take the square root and get 2/3, right? But it's a cube root. Multiply by the 3, get 12 27ths. Leave the cube root of 12 over 3. Are we good to go on at least the first one? On the next one, 7, since it's a prime number, it needs another 7 to get the 49. And leave the square root of 35, nothing else in there, all over 7. Good to go on the second one. Now 20, you could multiply by another 20 to get 400, but then you'd end up with the square root of 60 400ths, which gives you the square root of 60 over 20, and the 60 would have to factor into 4 times 15. Better to multiply by the 5 to get the 100. So try to get the smallest square you can. Did we end up with the square root of 15 over 10? All right, anyone leave square root of 60 over 20? Okay, good. All right, looking at this next one, the 108. I mean, it's a nice big one, and you say, well, maybe I could factor that. Again, it's not about factoring, it's about taking the root. So I'm thinking through my numbers here, and 216 comes to mind, since that's half of 216. So I just multiply by the 2. Cube root of 10, 216, so leave the cube root of 10 over 6. Do we get this for the fourth one? All right, is that where we got stuck? All right. Now, did you try making a list of your various cubes to try to use it as a trigger? Like, okay, 108 doesn't go into any of these. They're too small, right? 128 can't go into 125. Then as soon as you get to the next cube, that's kind of where we should have seen it. Did you try making the list of cubes? Oh, you were trying to turn it into something square. Oh, yeah. Well, 324, right? Multiply by a 3, and you would have had an 18 from the square root of 324. So I guess with a square root it could have worked, but yeah, a little easier with the cube root. And then for our final one here, we got the square root of 9 32nds. Again, don't multiply by another 32. Multiply by 2 to get 64. Square root of 18 over 8, and then that square root of 18 factors 9 and 2 to get 3, times the square root of 2 all over 8. Questions on this? Questions on this? All right, well, let's take a look at our final method of reducing radicals. Check your notes, make sure you've got this down, that we want a smaller index as our third means of simplifying or reducing radicals. And so the key is to rewrite the radicand as a power. I believe I gave that to you in your notes yesterday. Check to make sure you've got it. I did not necessarily mention this yesterday, as it was kind of crunched at the end of the hour, rather. But you only can make indices smaller if they are non-prime or composite indexes. So 2 can't be made smaller. 3, 5, 7, 11, those can't be made smaller. But 4th root, 6th root, sometimes 8th root, certainly 9th roots. Those non-prime indexes, when you see them, you should be thinking maybe I can make them smaller. So jot down that note as well there. Let's look at several examples together. Write this one down in your notes if you would, please. The 4th root of 36. Again, the key is to rewrite the radicand as a power. Noah, how could I rewrite 36? Six squared, right? And once we've rewritten the radicand as a power, remember I said that the key is, if we would make this a fractional exponent, it would be 2/4, which would reduce. We're too lazy to make the fractional exponent, but we see that I can take something out of the 2 and the 4. Or as I put it yesterday, all the little numbers. This is a big number. These are your little numbers, your little exponents and indexes. What obviously comes out of the 2 and 4? 2. So if I take a 2 out of a 4, and if I take a 2 out of a 2, 1. So really it's the square root of 6 to the first, or we could just say the square root of 6. We have simplified, we have reduced our radical. If you'll write this one down now, the 4th root of 121a squared. And I pointed out in our last example at the end of the hour yesterday that it's not just the numbers exponent, but rather all the exponents. Well, first of all, we didn't get an exponent. Brecken, how could I rewrite the 121? 11 squared. Again, we're not factoring it, we're writing it as a power specifically. So now, Brecken, kind of like last time, I say, well, what can I knock out of the 4 and the 2 and the 2? Something has to come out of everything. And what comes out of all that? A 2 again, to leave me with. So my answer, Brecken? The square root of 11a. Does that make sense? Now again, you'll notice this because you have big non-prime indexes, and you'll notice these are what I sometimes call special numbers. These are squares, these are cubes, these are powers of 2. Write this one down, the 8th root of 16. Maddie, thoughts? Good. Now this could be 4 squared, right? But she got something even better. She thought 2 to the 4th. Because now instead of canceling a couple of 2's, she can cancel a couple of, to leave herself with the square root of 2 to the 1st, or just the square root of 2. So sometimes it's beneficial to get something maybe a little bit bigger power, if possible. Write this one down now, the 9th root of 8m to the 6th. Noah, walk me through what we should do. Good. Rewrite the radicand, the number in the radicand at least, as a 2 cubed. Now, I've got a 9, a 3, and a 6. What can I knock out of everything? To get? The cube root of 2m squared. Great job. Are we starting to catch on here? At your seats, do this one, the 8th root of x squared, y to the 4th, z squared. At your seats. The 8th root of x squared, y to the 4th, z squared. No number to have to rewrite this time. That's kind of nice. And Brecken, give us your answer. How many had the same answer? The 4th root of xy squared z. Now there are students who will say, ooh, Mr. Dadaski, how about the 2 and the 4? Can I knock a 2 out of those? No, because you have 1's here and you can't take anything out of those. So you can't pick a single letter with something else. It has to be all the exponents, and the index have to have the something to cancel out. So we will leave our answer just like Brecken said, questions on that. Write this one down. Now the 6th root of a to the 6th, b cubed, c to the 9th. Maddie, thoughts? Okay, and what would that give us? Good. The square root of a squared b c cubed. That's as much as we can knock it down. But do you notice something now? Now that I've made the index smaller, go back to the first way of reducing radicals. How many times does this go into that, Maddie? Once, with nothing left. How many times does this go into that? Nothing, so we're going to leave the b. And how many times does this go into that? So remember with the fractions, we showed a moment ago how we may sometimes have to still use the first factoring method that, well, sometimes we may have to come back to this as well. We may not be finished just by knocking everything smaller. We may still be able to do more. Write this example down then. The 4th root of 324m to the 10th. Now I actually just mentioned this 324 number a moment ago, Noah. Thoughts? And this is why they've got to be memorized, right? It's 18 squared. So we're going to rewrite the 324 as 18 squared. And we have the m to the 10th. So again, the initial thought with a big index like this, a non-prime index, is let's see if we can make it smaller. And if we can rewrite the radicand as something to a power, then I can knock it down a little bit smaller. What do we get now? Good, the square root of 18m to the 5th. But I'm not done, because I can still now factor the 18. I didn't want to factor earlier. I wanted to rewrite it as a power. But now that I've gotten there, now that the index is smaller, now I can factor the 18. 9 and 2. Yeah, 3 and 6 technically works for factoring, but you can't take the square root of either number, right? So we're going to factor this into 9 times 2 times the m to the 5th, where no, I'm going to take the square root of the, to get, we're for now going to leave the 2, and then we can get to the letter and ask ourselves, how many times does 2 go into 5? Notice, initial step, get here. Final step, reduce it down. Do we see how there's going to be some two-step to this reducing of radicals? Questions on that? Let's do another one like this. Let's do the 6th root of 121, a to the 6th, x to the 4th. And Maddie, walk us through this problem. Good. Start by rewriting the 121 as an 11 squared. As soon as you see a big index, see if you can rewrite as a power. We can. Then what? I had a hard time catching everything you said because you talk so quietly. It sounded like you started to say factor and then realized you couldn't factor, which is fine. You're looking at these letters here, and obviously I can't knock a 3 out of everything, right? Because for one thing, there's a 1, a 3, and a 2. 3 doesn't come out of all of those. But there we go. The 3 does go into the 3 one time with nothing left, so I can at least do that much more. Do we see how to look at the problem? Once we've done the initial step, realize that maybe all it is an initial step. We may have to go a step further. Questions on that one? One more of these, the 9th root of 343, m to the 6th, n to the 12th. The 9th root of 343, m to the 6th, n to the 12th. Brecken, thoughts, walk us through. Well, with a big index, we don't want to factor, we want to rewrite as a power. Something squared, something cubed. Good. Add up the first 2 digits or the last 2 digits. 7 cubed, okay? So we're going to rewrite as 7 cubed, m to the 6th, n to the 12th. Okay, continue. Good. All right. You said 3 goes into 4 one time with 1 left over. There we go. And that'll be our final answer. Questions on this? We feel like we kind of got the hang of this now. All right, turn your textbooks to page 302. Page 302. I want you to do the review numbers 13 to 16. Page 302, the review numbers 13 through 16, making the indices smaller. And again, you can do this with any index that is not prime. I will confess, these problems are not actually great examples, but I didn't look at them super closely. They looked like what I wanted, and now I'm actually writing them on the board. I'm like, actually, these work out kind of weird. Let's talk through these together, and then we'll get to another assignment that has more of what we were looking for, because 81, class, what is 81? It is 9 squared, right? But it's also 3 to the 4th. And if that's the case, then class, I could knock out a 4 from everything. But then I don't have an index anymore, which means I don't have a radical, which means I just get 3x. Similarly, on the next one, how might I rewrite 16? 4 squared, or 2 to the 4th. So what do I get for an answer here, Noah?
2y squared.
Well, 2x, 2 to the first, x to the first, y squared, right? Because the 4 goes into all of those evenly. 2 to the first, x to the first, y squared. So, yeah, that one didn't really work out so great either. Now, the next one's fine. The next one, Brecken, we would rewrite the 8 as 2 cubed. And then we have the x to the 12th y cubed. And then to get the square root of 2x to the 4th y. Then there's one more thing we can do. Well, take out 2 x's, right? 2 goes into 4 twice, so we can take out 2 x's and leave in the 2y there at the end. So this was actually the only example in here that was truly what I was going for. I just didn't account for that too well. Questions on these first few? Now here I already knew this one wasn't going to be so great because thoughts on the 5th root, class? That ain't prime. I mean, that is prime, excuse me. You can't make that any smaller. Thoughts on the number 243? We've seen it a few times this year. Right, Gavin, that's 3 to the 5th. But is there anything I can knock out of these indexes, though? But I can say 5 goes into 5 one time with nothing left. 5 goes into 2 no times with 2 left. 5 goes into 10 2 times with none left. And so that's actually how we would work that problem there. Questions on these? Again, a little bit different, not quite what I was expecting them to be. Questions on this? All right, turn back to page 297. Turn back to page 297. These actually will work out much more like what I was going for. Page 297, 33 to 36. Page 297, 33 to 36. Try to finish early, do 40 and 41 as well. Finish early, do 40 and 41 also. All right, for sake of time, pencils down, even if you're not finished. Let's take a look at these and see how we did on the ones we got to. Maddie, we'll start with you. What do we do? Good, rewrite as 5 squared. Square root of 5. How many have the same answer? On the next one, Noah, walk us through. Okay, rewrite as 6 squared. root of 6. Good to go on that one. On the next one, Brecken.
27 to 30.
All right.
Take the 3 out of everything.
Well, not this one, right? Like the little ones, okay? There we go. We get the square root of 3x. All right, on the next one, Maddie. Good. Rewrite as 11 squared, which we still have the x squared, y to the 8th, and z to the 4th. Out of all 5 things, good. Finally, remember that 2 goes into 4 twice evenly, 2 goes into 2 once evenly, leaving us with the square root of the 11x. Did we get this answer on number 36? Did we finish it out? Good. Look at this next one, Noah. Number 40.
16, 20, or 17.
17 squared.
And then you cancel the 2 and 4 to get 17 squared. Or square root of 17.
Square root of 17 should have been our answer here. Anyone else get that? You did, good. And then this last one here, Brecken. And while 9 is a great square root, it's a horrible cube root, so we're just going to leave it. Can't do anything else with it. And there's our answer for 41. Did we get that for 41? All right, questions at all on these? Now, here's the fun part, folks. Figuring out what to do when. Basically, when in doubt, the top method. Factor up the number, take the roots of factors. If it's a fraction, then you know you have to take the root of the denominator. If it's not a fraction, obviously you don't do that because there ain't no denominator, right? And the only time you try to get a smaller index is if you got a big index that's not prime. So if you don't see a big index, that ain't what you're doing. If you don't see a fraction, you ain't worried about the denominator. It's the first method. But you've got to pick and choose what to do when on the homework handout this evening. You also have a 2-digit number word problem on the homework handout as well. We'll take a look at this tomorrow in our next lesson, and then we'll be taking a quiz over reducing radicals in our next lesson. Have a wonderful rest of your day, and you are dismissed.